All right, so this is going to be a tutorial video for section 16.6 day 2. If you remember 16.6 day 1, we started looking at just some various examples of parametric surfaces, and we used CalcPlot 3D in order to explore those a little bit. And remember, I encouraged you spend some time on your own actually going through adjusting the parameters, rotating the surface, just to get some intuition for what the grid lines are showing if you fix a value of u, if you fix a value of v. The rest of this chapter is going to be a lot easier with the more intuition that you have behind understanding those parametric surfaces. So anyway, we're going to move on now and actually do some calculus with it. And the first thing we can do is we can write the equation of a tangent plane to a parametric surface. Now, we wrote equations of tangent planes last semester. That was when we had functions or surfaces of the form z equals f of x, y. Now we're going to do it parametrically. Okay. So this allows us to kind of expand the different surfaces that we're looking at and not just look at surfaces of this form. So if you remember from the other day, let's say that we have a vector valued function, r of uv equals x of uv, y of uv, z of uv. You could write this in component form also. And give me 1 second. Okay, so we want to find a tangent plane to this parametric surface S that's traced out by this vector valued function. We're going to pick a specific point. We'll call it P naught, which has position vector R of U naught, V naught. So the idea is that if we keep U constant, so let's fix a value of U, call it U naught, then really the only variable that's changing is V. And so what we do is we can take a partial derivative of this vector valued function with respect to V that has these components, partial x, partial V, partial y, partial V, partial Z, partial V, at the point U naught, V naught. And that's going to give us, it really, this vector valued function then just becomes a vector function of one parameter V, and it gives us a grid curve on the surface, which is S. Okay. The tangent vector to C1 at that point is obtained by taking the partial derivative of R with respect to V, as shown here. Similarly, let's say you keep or you fix a value of V, let's call it V naught, then the vector valued function that's left really is just a function of, this should say U. Okay. Becomes a vector function of the single parameter U, and that defines a second grid curve. We'll call it C2, lying on the surface. And so the tangent vector to C2 at that point is obtained by taking the partial derivative of R with respect to U, since U is the only variable that's changing. Okay, so similar structure to the one above, except all these partials are being taken with respect to U. So we call these RV and RU. Okay. Here's a visual of what I was talking about. Okay, so if you fix this value, U equals U naught, say this is in the UV plane, right? Here's my value, U equals U naught. If I go to XYZ space through the parameterization, here's my grid curve C1 that you see outlined in pink. And then if I do another one, let's do this one in, I'll do a light, like a light green maybe. Here's V equals V naught, fix a value of V. That's going to go to a separate grid curve, C2. Right, and then these intersections right here, here's my point P naught that I'm interested in. I get one vector going this way. There's my R sub V. That goes with grid curve C1. And then I get my second tangent vector going this way. That's R sub U, and that goes with grid curve C2. Okay. And so a couple hypotheses here. If RU cross RV, and think about what would that be giving us? This is going to give us some type of normal vector, right? Anytime we took a cross product of two vectors, it gave us a normal vector to the surface. We're going to need that in order to write the equation of a tangent plane. So we don't want that to be 0, though. Otherwise, we don't get a tangent plane. So as long as that's never 0, we call the surface S smooth, which just really means, if you remember from last year, we talked about sharp turns or cusps or corners. We just don't want this surface to have any corners. Okay? Nice and smooth. For a smooth surface, the tangent plane is the plane that contains the tangent vectors RU and RV, okay, as shown here. And so then the cross product of those two vectors, RU cross RV, would be the normal vector to that tangent plane. So if I kind of sketched it here, you know, it'd be like a vector coming up. There would be your normal vector would be RU cross RV. Okay. So let's try an example. So let's find the tangent plane to the surface with parametric equations x equals u squared, y equals v squared, z equals u plus 2v at the point 1, 1, 3. You could put this on CalPlot 3D. This is actually a pretty cool surface. It's called a self-intersecting surface. So it actually crosses through itself while still remaining one piece. And you can kind of see a small side view that I snipped of it there. But actually go on CalPlot and take a look at it. It's pretty cool. It kind of slices through itself. And we want to find this tangent plane at the point. Now, keep in mind, this point is given in terms of x, y, and z. So we're going to have to figure out, you know, what u value are we using and what v value are we using. And we can actually probably figure that out right now. You know, u and v technically could take on values of 1 and -1 to produce the first two coordinates. So it's that z value that's going to help you narrow it down. If u and v were both negative, you would end up getting the point 1, 1, -3. So u and v can't both be negative. So in this case, we want u equals 1 and v equals 1 in order to give us x equals 1, y equals 1, and that gives us z equals +3. Okay, so you got to make sure that you're careful about that. So this would give us the u and v value that we're going to be interested in evaluating at. Okay, but process, what do we need? Well, we need a normal vector. So we're going to need to calculate RU and RV. So if I take the partial of R with respect to U, so this is going to be dx du, dy du, dz du. I'm going to end up with, erase some of this stuff off to the side here. So we'll keep track of that. So we said U is going to be 1 and V is going to be 1. We get 2U, we get 0, and we get 1. And then I'll do the same thing with V. RV is going to be dx dv, dy dv, dz dv. And we get 0, 2v, 2. Now I got to take the cross product, RU cross RV. And we just go alphabetically. We use U first, then we use V. I, J, K. We're going to put our components here, 2, 0, or 2U, 0, 1, 0, 2, V, 2. And then we'll do our crossing off of rows and columns like we've done in the past. So if we do that, cross off first row, first column, we get 0 minus 2V. Cross off first row, second column, we get, and remember to flip the signs here, right? It's going to go positive, negative, positive, like we've seen with cross products. So let's make sure we make that negative. We're going to get what? Negative quantity 4u minus 0. And then we end with crossing off first row and third column, we get 4uv minus 0. So this gives me negative 2v. Make sure my v's don't look like u's. Negative 4u, 4uv. And as we said, we want to evaluate this. This is a normal vector to the surface, but we need to make sure that we actually plug in u equals 1 and v equals 1 into this cross product. This is the general formula for the normal vector. We want to evaluate it when u equals 1 and v equals 1. So we'll call this n, our normal vector. So I'm going to plug in 1 for u and v in the thing I highlighted. I get negative 2, negative 4, 4. And we could use any scalar multiple of that. So I'm going to divide everything by 2, and I'm going to use negative 1, negative 2, 2 as my normal vector. And so then my tangent plane, okay, passing through the point 1, 1, 3. So remember, how do we write the equation of a tangent plane from last semester? We take the normal vector and we dot it with x minus x naught, y minus y naught, z minus z naught, and those are orthogonal, so that dot product has to be 0. So if we expand that, we're going to get -1 times x minus 1 minus 2 times y minus 1 plus 2 times z minus 3 equals 0. And if you expand and clean that up, you can do some of the algebra. You get x plus 2y minus 2z plus 3 equals 0. So it gives us a linear equation of that tangent plane. So that would be my tangent plane. Okay, so not too bad. Okay, so the next thing we want to do is, what if we want to actually find the area of these parametric surfaces? How do we find the surface area? We're going to define it in a similar way that we did in section 15.5. We did look at surfaces of a specific form when z was equal to f of x, y. Now we're just doing it in general. So we're going to take a little rectangle in the UV space, okay, that has width delta U and length delta V. So I'm focusing on this little rectangle right here. And I'm going to map it over to XYZ space, and it creates this little curvy piece right here. And this is what's called a patch. And this is reminding you of stuff we did, and take a look back at section 15.5. Okay. We did something similar here. Okay. And so we want to figure out, how do we find the area of one of those patches? Because if I can find the area of one patch, and then I sum across all these patches, essentially what I'm going to get is I'm going to get an approximation for the area of this surface right here, which is S. So I'm going to focus on one patch and see what I can do with that. Okay. So we're mapping a small rectangle in the UV space to a small little, it's like an approximated parallelogram, right? It's got some curviness to it, but we're going to use a parallelogram to approximate it. And that little curvy parallelogram is what we call a patch. That's what I outlined on the last page. So to find the area of one of those small little p-grams, I'm just going to sketch it up here. Here's my little patch. Okay. Well, we've done this trick in the past. To find the area of a parallelogram, you can take the cross product of the two vectors that span that parallelogram. So here's my two vectors in blue. I'm going to outline. Okay. This one was being determined by or we need to know the tangent vectors, right? Yeah. We need to know the tangent vectors forming the sides of those parallelograms. So that would be, I'm going to call it r sub u star, because I'm taking a specific point inside, and r sub v star, any sample point you want to take from the rectangle. But we're scaling them by the length of that rectangle. So they're going to be scaled by delta u and delta v. So this would really be delta u times r sub u, and this would be delta v times r sub v. And this would be my patch. Okay. So to find the area of one of those parallelograms, we need to calculate the magnitude of the cross product of those two blue vectors that I sketched up top. Magnitude delta u, r sub u star, cross delta v, r sub v star. And the result is coming. I just want to show you where it comes from. Okay. You don't need to get super caught up in all this notation. So if you go through the calculations for this, you can actually, you're going to end up with a square root of, you're going to have a delta u squared delta v squared. So it's going to come out as a delta u delta v. So this is just going to give you ru cross star cross rv star delta u delta v. And so then if we sum across all those patches, I can sum from 1 to m. I can sum from j equals 1 to n for both directions of this magnitude, ru star cross rv star delta u delta v. This approximation, as usual, is going to get better as we increase the number of subrectangles. And so then it turns into a double integral. Okay. Not a big surprise. We've seen this a lot this year. And so that's going to be how we find the area of our surface, right? So let's assume we have a smooth parametric surface S given by that vector valued function R. Okay. And we assume that S is covered just once as UV ranges throughout the parameter domain D, so that we're not overlapping it more than once. Then the surface area of S is given by double integral over our domain D of the magnitude of the cross product, RU cross RV, partial with respect to U of R cross partial with respect to V of R, okay, dA. And so this dA is either du dv or dv du, depending on which way that you integrate. R sub u and R sub v are defined as we did on the previous page. That's just the vector of partials of R with respect to u and v. Okay, so let's do an example here. Okay, so find the exact area of the portion of it's called a spiral ramp. Again, go on CalcPlot if you're interested in taking a look at this. I went on there, graphed it, and I snipped it for you. You find the exact surface area of the portion of the spiral ramp given by this vector valued function. R of uv is equal to quantity u cosine v for the first component, u sine v for the second component, and v for the third component. And we're assuming that u is bounded between 0 and 1. Now, v is not bounded between two constants. It's bounded between actually 0 and u. So when you look at the surface here, it's not quite the entire green thing that you see. This line right here, I'll outline it in pink. This would be your line v equals u. So what we're really interested in is we're interested in the surface underneath that line when v is less than or equal to u. So really this little surface here, and I don't like that's not showing up as pink like I want it. Let's do like light blue. Yeah, it's this little surface. Oh man, it's really not. I'm just going to outline it. This is what we're finding. We're finding the area. This is our surface right here that we want. Okay. And so basically ignore that part over there. That's above the line. We want v to be less than or equal to u. So what we're going to do, eventually, goal, is we're going to want to have the area over D of magnitude RU cross RV dA. This is going to give us the area of the surface. So we got to kind of build the pieces. So let's take R sub u and R sub v. R sub u is going to be cosine v, sine v, 0. R sub v is going to be negative u sine v, u cosine v, 1. RU cross RV, ijk. Put those components, cos v. Make sure you're very careful about labeling your u's and v's so you don't get lost here. As soon as you mess one up, the calculation goes awry. Okay, so what do we get? We get sine v minus 0 would just be sine v. We get negative cosine v minus 0. So negative cosine v. And then we get u cosine squared v minus negative, so plus u sine squared v. I see a sine squared plus cosine squared, which is 1. Definitely clean that up. It's worth it. So I get u times 1, which would be u. So that's my general normal vector, right? Now I need the magnitude of that cross product. Notice we're not evaluating at a specific point like we were when we were doing the tangent plane. We're finding the area of this surface for many different values of u and v. So I'm leaving this right here. I'm not plugging in a specific u and v value. That's an important distinction from what we did with the tangent planes. So this would give me square root of sine squared v plus cosine squared v plus 1. Hey, this thing right here, we like that. That's 1. So this is rad 1 plus 1, which is rad 2. All right, so the area of my surface is just going to be double integral over D of that magnitude of that cross product, which is going to be, oh, sorry, that's not rad 2. Losing it. U squared, I'm sorry. So this would be still a 1, but it's not 1 plus 1. It's rad 1 plus u squared. There we go. So this guy right here is going to go inside my integral. That's my magnitude of my cross product, dA. I think I'm going to go dv du as my order of integration. So 0 to 1, v goes from 0 to u. Rad 1 plus u squared dv du. So I get, let's see, 0 to 1. We're going to get, antiderivative is going to be v rad 1 plus u squared, plugging in 0 and u. We're going to get what? U rad 1 plus u squared du. Probably come up to the top here. Let's give myself some space. I would do a u sub, but I wouldn't call it a u sub because you're already using the letter u. I'm going to erase this part. So let's call it a w sub. Let's let w equal what's inside the radical. So 1 plus u squared. So then dw will be 2u du. So 1/2 dw would be u du. So we're going to get changing bounds. Let's see. Now we're going to go from 1 to 2. There we go. Pull our 1/2 out front, and I'm left with square root of w, or w to the 1/2 dw. So I get 1/2, raise and divide. Raise the power by 1 would be 3/2. Divided by 3/2 would be times 2/3. Cross those out. W to the 3/2 from 1 to 2 would give me 1/3 times, this would be 2 to the 3/2 would be 2 rad 2 minus 1 to the 3/2 would be 1. So that'd be the area of that portion of that spiral ramp. And as I said, go on Calplot 3D and actually take a look at it, see why it's called a spiral ramp. You're only looking at a small portion of it, but it does end up spiraling. It's kind of a cool shape. Okay. Consider the special case where z equals f of xy. Xy is in the domain space D. Let's find a formula for the surface area of S over D. Okay. So you're going to see this show up a lot in the last few sections. We're going to look at these special cases where z is a surface defined as a function of two variables, x and y. Anytime you see this, what you're going to do is you're going to use the trivial parameterization. This is the special case of using a trivial parameterization. So we're just going to let r of xy be xy f of xy. Okay. Easiest parameterization you come up with. So what would r sub x be? R sub x would be 1, 0 f sub x of xy. And r sub y would be 0, 1 f sub y of xy. Taking our cross product, rx cross ry, get ijk. 1, 0 fx, 0, 1 fy. And so we get, let's see, cross off first row, first column, we get 0 minus fx times 1, so negative fx. Cross off first row, second column, take the negative, fy minus 0, but change the sign, so negative fy. And then cross off first row, third column, 1 times 1 minus 0 times 0 would be 1. Okay. So it looks like this is what this is our normal. So our normal vector takes the form negative f sub x, negative f sub y, 1. Okay, so that's an important point. We're going to see this a lot in the last few sections. Our normal vector takes on that form. Okay. This is a normal vector just in terms of x and y. And then you could plug in any specific point that you want. Okay, so we need the area of this surface. So we need the magnitude of that cross product, rx cross ry. So we're going to end up with negative fx squared would be f sub x squared. Negative f sub y squared would be f sub y squared. 1 squared would be 1. And notice these could be written as partial f partial x squared. And there's a reason I'm doing this, because you're going to see this is actually something we've done in the past. So the area of my surface, so therefore, it's the double integral over d of this thing right here. 1 plus partial f partial x squared plus partial f partial y squared dA. And this domain is in xy space. Well, now it's been a while, so I'll forgive you if it doesn't look so familiar, but it should, if you take a look back at your notes, this should look familiar because we actually did this in section 15.5. So in the special case where S is defined by z equals f of xy in this domain space D, okay, there's our result that I just wrote down. This is exactly what you had this on a quiz and a test. We just only focused on that specific case in 15.5. What's cool about doing this now, it's a common theme in this course, is what we're doing is we're encountering things in this course that are really just special cases of bigger or more general ideas. So the special case in this case is taking a function f of xy. The bigger or more general idea is using a general parametric surface R of uv. And so you're going to see this pop up throughout the rest of this unit. Chapter 16 is where this really all comes together. Everything we're doing, there's a lot of cases in this course already where we looked just at special cases, and now we're generalizing to a very broad setting. And there's a lot of big theorems coming up, like Stokes' theorem, and some other theorems that we're going to do also that are really just generalizations of things that we've already talked about. So it's really, chapter 16 really makes it all come together. It's pretty cool. And everything we've done in 16.5 and 16.6 are really going to be the building blocks we need for the rest of the chapters. So in 16.5, we talked about curl and divergence. Curl is going to play a very big role in Stokes' theorem, and divergence is going to play a very big role in the divergence theorem, otherwise known as Gauss's theorem. And 16.6, we've been looking at parametric surfaces and their areas. This is going to play a big role in surface integrals and flux integrals coming up in 16.7. Okay, so lots of background information we need to be able to do the cool stuff for the rest of the chapter. If you want some practice with this guy, we did a lot of this in 15.5 already, but if you want to see an example, we actually did this one in 15.5. I'm going to run through it one more time here. If you feel you can handle that, you can kind of stop watching at this point and work on some homework. But if you want to watch me walk through this one, I'll do this one. Okay. Find the area of the part of the paraboloid z equals x squared plus y squared that lies under the plane z equals 9. Okay. So kind of what you're looking at. Here's your paraboloid. Once the plane slices through it, there's the plane z equals 9. We're looking for just the area right here of this surface. That's S. Okay. And that's given by this equation. Z equals x squared plus y squared describes that surface. Okay. So our domain, if we project this down into the xy plane, here's D. I'm going to sketch it over here in R2. It's a circle. It's the circle x squared plus y squared equals 9. And really, we're looking at the interior of it here. So we're going to do x squared plus y squared is less than or equal to 9. That's going to allow us to do the integration. All these intercepts are -3 and 3. Just label my axes there. Okay. Yeah, so if we plug in our formula, and we could go through this process from scratch, and that's another thing I want to point out is if you forget this, the point here is not to memorize every single formula. I know there's a lot of formulas in 16. That's why I treated this kind of as an example. You could always just run through this from scratch, do the parameterization, and you'll get to the exact same result. So don't worry if this is like the one thing you don't want to have to memorize. Don't, just run through the parameterization. This didn't take too long to do. But I am going to go to the result just to save some time here. We're integrating over d. Square root of 1 plus, this will be dz dx squared, plus dz dy squared dA. So this will give me double integral over d. Let's see. Partial z partial x is 2x, and partial z partial y is 2y. So 1 plus 2x squared quantity plus 2y squared quantity gives me double integral over d of, we're going to get a 1 plus 4, and I'm going to factor the 4 out. I think you'll see why, because this is a pretty nasty integral to do in Cartesian coordinates, but we like x squared plus y squared because that's polar. So I think I'm going to switch this to polar coordinates. Okay. So I'm getting the full circle going all the way around. So I know theta is going to go from 0 to 2 pi, and I can see the radius is going from 0 to 3. So in polar, that's going to be my polar bounds. So I got 0 to 2 pi, 0 to 3. Let's see. So we're going to get definitely that extra factor of r, dr, d theta. 1 plus 4, and apologies, this should be r squared, not r. X squared plus y squared is r squared. So 4r squared, dr, d theta. Okay. Remember that property, you can split this up since it's numerical bounds and it's a product of a function of r, and the function of theta would just be 1. So this would be dr. So definitely this part in front is just going to give us 2 pi. You could do the u sub if you want to. This would be, let's see, u would be 1 plus 4r squared. Du would be 8r dr. So 1/8 du would be r dr. So really what we're going to end up with here is this, well, there'll be a 1/8 in front. And then we're going to have u to the 1/2. And then this will just be our du. Yeah, so we've really just got that. And then if we raise and divide, we're going to get u to the 3/2 divided by 3/2, so times 2/3. I think I'm just going to put it back in terms of r. So this will be 1 plus 4r squared. That way I don't switch my bounds from 0 to 3. And if we do that, same example we did a while back, I need some space here. This is going to be, you can do some cleanup on your own later if you want. This will be pi over 6 times 37 rad 37 minus 1. And I'll say or any equivalent exact answer. You don't have to exactly have it look like that. Pretty messy. You're going to see that with a lot of these calculations we do in the later sections. They're not super clean. But at least that gets us started. We're going to do a lot more cool stuff. This is kind of the background info that we need, our tangent planes and area of a surface to be able to do things in 16.7 like surface integrals, which are very similar to work integrals, but we're using a surface now instead of a line integral, and flux integrals. So pretty cool stuff. All right. That should do it for this section. Hope that helped, and you can get started on your homework.